We're going to take on a journey into silicon reverse engineering of digital synthesizers of the 80s and 90s and uncover silicon secrets. Giulio is an Italian hacker, web developer in his day job, with a kink for reverse engineering of vintage technology. Please give him a warm welcome.
Hello. Hi, can everybody hear me? Nice, so let's start. Today I wanted to bring to you this topic about proprietary silicon ICs and dubious marketing claims. Let's fight both of those with a microscope. So what are we talking about? I don't need to introduce what silicon chips are, but we know that they're pretty much everywhere, in your phone, in your computer, in your washing machine, in your air fryer, in your car, but also some things that I especially like, which are, for example, video games or musical instruments. And that got me interested. The thing about silicon chips is that some of them are very well documented. We know very well how they work internally. We know how to write software for them. We know how to emulate them. And that's really nice. For example, here the CPU from an Arduino, it's fairly well documented. There are other chips that are not so greatly documented. If we take, for example, a gaming console like the first PlayStation, it is kind of documented because the SDK for developing it leaked, and we know basically now we can emulate it perfectly, but we had to go through some hoops of understanding how it works. For other things, it's like a complete mystery. If we take like an arcade game, we can see that we have 1, 2, 3, 4, 5, 6, 7, 8, 9, probably 10 custom chips. And we like arcade games. We want to be able to play them again, especially when all the hardware dies. If everything is custom and undocumented, that becomes a bit complicated. But also with musical instruments, if, for example, we take something like a synthesizer, like the Roland JP8000, it uses one of those chips, which is a custom DSP, which runs some proprietary bytecode. And so far, we have no idea how it works. It will be a shame if, when all the hardware dies, we are not able anymore to play instruments like those, especially since they are completely digital. They should be emulatable. So why studying this stuff? Why studying silicon chips? Well, because electronics die, we want to preserve it. And also because when we look at electronics and software from the 80s and 90s, I found it very fascinating because they had to overcome a lot of limitations of the hardware, and so they figured out a lot of tricks, which now we don't care about anymore in the age in which we have infinite memory and infinite compute. But I think it's still cool to see how they did things back then. So before going forward, I have to bring a little disclaimer, which is I have probably no idea what I'm talking about. As said in the presentation, I'm a software engineer. I work mostly on TypeScript, so I had to teach myself some electronics, because otherwise, like, I did computer science, I don't know much. But there is one specific reason why I did this. And at a certain point, I was hyper focusing on looking at old stuff and old keyboards, and I found this bad boy. The RD1000, it's a keyboard from 1986, which is like regarded as one of the very first digital pianos that were ever made. And nobody seems to know how it works. Like, I took this from a newspaper from the time, and they were talking about how details about the inner workings of this thing has been a bit of a mystery. And apparently, they sampled 88 notes of a piano, and then they processed the waveforms on a mainframe, and then they put everything into a single VLSI chip. So I was like, what? like, is this something that probably now we figure out how it works and we can emulate it? Well, no, nobody still knows how this works, and this bothered me a lot. So, what did I do? I looked at the schematic, and I was in panic because it uses a CPU, 3 RAM chips, 1, 2, 3, 4, 5, 6, 7 ROM chips, and 3 completely custom chips, even with the pin names removed. And I couldn't figure out much from this. And so my initial reaction to this was, what is going on? So much for the single VLSI chips, those are 3 of them. What are those chips doing? And my second reaction was pretty much this, and wanting to be the first one to explain to the world how this thing works. So what did I do? I found one to buy for cheap, and have it here with me, which of course doesn't have most of the chips anymore, because they've been sacrificed for a greater good. And what is this greater good that we're talking about? Putting them in acid. It's cool because you can take those chips and dump them into very hot acid, and then take very nice pictures of them with a microscope, which, if you know what you're looking at, you can understand a lot of things from them. And I didn't do this part because there are people that are far more knowledgeable and risk-taking than me, like acid is dangerous. And so I sent them to a very nice guy, which sent me in return those pictures. And so finally, for the first time, we were able to look at those chips and see how they work inside. So, from a picture like this, can we finally uncover this mystery and figure out how that thing worked? Kinda. There is... here we go into the art of silicon reverse engineering. And silicon reverse engineering, it's a thing that works because of this principle that was stated in a circuit design book, which, if you want to understand at least qualitatively how a chip works, we don't need to know all the physics and the manufacturing details, but it's enough to be able to differentiate among certain types of materials, like metals, that are the conducting wires, polysilicon, and strongly and weakly N and P doped semiconductors, and non-conductive dielectrics. If you look at this picture here, which is from a Thomson gate array chip, on the very edge of the chip, they added this kind of legend, probably to verify their own production process, in which they named the different materials with the material itself, so you can basically understand which layer, what color is it represented in the microscope picture. And I think that's really cool. So the base principle, the base unit which those devices work is CMOS, which is what technology that they started using pretty much everywhere after a certain point in the 80s, which stands for complementary metal oxide, and basically means that you can use 2 devices called the PMOS and the NMOS transistor to implement logic. The idea is that those devices work like switches. One specific device can turn something on, and another device can turn something off. I'm explicitly avoiding naming which one because I will mix them up. So I will let the slide talk for this. And with using those NMOS and PMOS, we can implement logic gates. And if we can implement logic gates, we can implement pretty much everything, since they can be pretty much Turing complete. And the idea is that if we find how those logic gates, how those CMOS gates work in the silicon, we are then able to reconstruct what is the logic equation of the chip, basically how it works internally and what turns something on and what turns something off. And this is an example of a NOT gate. in which the input just gets inverted. And that's an example of how a NOT gate could look if we are looking at a specific silicon chip. Of course, there are not only NOT gates, there are other things that are way more complicated. For example, NAND gates and NOR gates. And with those, pretty much, we can build everything. Now, I'm not going too much into the detail of this, but if you want to learn more, on the Silicon Prawn website, there is an amazing CMOS quiz, which basically guides you from looking at that specific picture to finally understanding what that chip does, which is really cool. But maybe we don't need to necessarily look at all the single logic gates to understand stuff from chips. When we look at the die shot, it's called, we can a lot of times recognize specific devices and by just looking at it from above and maybe like figure out a lot about the chip just by looking at it, not at a transistor level, but a much higher level. Let's talk about some examples. A lot of chips inside, once you microscope them, you can find a structure like those. And that specific structure there, it's a ROM. That is a thing that contains data. You can give it an address and will return you a specific byte. And those ROMs sometimes contain a lot of very important data, such as lookup tables or encryption keys, microcode. The thing with decryption keys is especially important because in some arcade games, the game itself was encrypted and the key to decrypt it was stored in a ROM inside a chip. So this is extremely important because even without looking at the transistors, we can look at those patterns and figure out which one is 0 and 1 and dump the keys this way. Unfortunately, it's not always that simple. There are some ROMs, like this one, which are very easy to read. Other ones which are more dangerous to read. Some of them, to be able to mark the 0 and 1 bits, require some dangerous chemicals, such as hydrofluoric acid, or you need delayering, which means removing a few micrometers of surface from a chip by sanding it off. This gets complicated, but thankfully, that's not always the case. Or not everything is ROM. Sometimes you also find RAM. And by looking at RAM, you can figure out, okay, this chip has an internal memory, so it must be storing some information, like a program. And that way we can figure out how big the program is and how many bits it's using by counting the data and address lines. So that's another qualitative chip that you can, another qualitative thing that you can understand from a chip. Another thing that you can figure out is the pinout, because sometimes you don't have any information about what are the pins of a chip. But if we look at the edge part, where the connections are, we can maybe figure out which pins are input, which pins are output, which one are just power or ground. And that's another thing that can tell you very important things about the chip, especially when you don't know anything about it. But what if we want to understand actually the logic, how it works? Well, then it depends on the type of a chip. Let's start from the simplest one. Those were really popular in the 80s and 90s, and they're called gate arrays. The idea is that they are a pre-made die that can be customized by adding 2 final layers on top. It uses a pattern in which the N, P, and poly regions are always the same. It's basically a blank canvas. And then you just customize the wirings on top, which is kind of similar to how modern FPGAs work, just that this is basically hard-coded on the silicon. And those are basically the easiest to reverse engineer of all the types of silicon. Let's zoom in, let's look at how those cells work. Basically, the chip is made by several rows of those basic cell, and that's an unused one. And we can see already a few interesting features from this. One, for example, is metal wires, which conduct electricity or signals, and those 2 vertical wires are power and ground. And we can also notice that basic cell, and we can also notice vias, which are connections, holes that go from one layer to another. And that specific basic cell, it's implementing, in this case, 4 transistors. What we see here is that that green part, it's polysilicon, which is a material out of which the inputs are made of. And those intersection pieces, I can't point, but where I wrote PFET and NFET, those are 4 transistors that can be used. And then depends what you connect, like how you put the wires on top of them. For example, that's the electrical symbol of it, and depending on how we connect the wire on top, we can implement different logic gates. One example, if you go a bit higher, we can see how that's a logic part built with one basic cell, which has one input and uses just 2 transistors, one N and one P, and then it goes into one output. That specific configuration that uses 2 transistors, one N and one P, it's implementing a NOT logic gate, which is an inverter. And that's a simulated version of it. Of course, that's a very simple logic gate, but if we combine together multiple basic cells, we can implement much more complicated stuff. Like, for example, this one, it's a 1-bit flip-flop, which is a device that can maintain 1 bit of memory in practice. So the cool thing about gate arrays is that they use all those kinds of more complex cells, which are pretty much always the same among the same manufacturer. So if I find multiple chips that were always made by the same company, then they probably reuse this library over and over, and I just need to reverse engineer them once, because then basically I already understand how that specific cell works. It's like figuring out the ISA, the instruction set of a CPU. Once you figure out how a single program works, then it's very likely that you are also able to understand other programs for the same architecture. And this is a thing that thankfully helped me a lot, because out of all the possible cells, there is thankfully a data book from 1989 for those specific chips, which for each possible cell, for example, multiplexers, adders, it tells me exactly how many basic cells it's using. So basically, if that thing it's only using 1 basic cell, it means that I know every single cell that it's using just 1. So I can quickly rule out all the ones that definitely are not when I find a new one. And so what did I do? I created a giant spreadsheet with all the possible different cells that I could find. And now I'm like 90% of all the ones that are possible. And basically I merged together my work and work that a lot of other reverse engineers have done. So basically it means that if you find a Fujitsu gate array, you can use this spreadsheet to figure out every single cell, and you just have to see how they connect together. Thank you. Unfortunately, this is just for Fujitsu. Suppose that you find an NEC gate array. Well, you have to redo all the cells from scratch. Or a Toshiba gate array. Well, good luck with that. And those are gate arrays, which are easy to reverse engineer. But unfortunately, a lot of other chips were made with a different technology called standard cell, which means that they don't have this repeated structure, but they are also changing where the NP and poly regions are, which means that it's even more complicated. But thankfully, we can still build like a kind of lookup library. But we see something very cool here. Let's zoom in. As I said before, we can also find specific pattern before looking at the transistor themselves. This one, for example, is a DSP multiplier. It's a part of the chip that can do multiplications really fast, And by really fast, I mean that you put the 2 inputs and it gives you the output combinatorially. Of course, it takes a big part of the chip because it needs to do a lot of additions. Or if we go down here, we also see a mask ROM that we can dump. So we can also dump data from here, and we also see static RAM, which we can maybe understand something from it. But if we look at the cells themselves, they are a bit more complicated. We can't rely on the repeated structure anymore, but we need to go there and do some further reverse engineering for each one. This one, for example, is one that I started reverse engineering, and I found some cells, and then I marked each N and P transistor and saw how they connect together. And with that, I figured out that one is an inverter, and another one, it's 2 ends that go into a NOR with a NOT, which it's called an AOI port. So it's a lot of work, other stuff that you have to reverse engineer. And that's just for Fujitsu. If you go into Toshiba, you find different cells, which are even more densely packed, and it's even more complicated to find out what's going on. The very, very cool thing is that this chip has been completely reverse engineered, which it's crazy given how complicated it is, and some people in the scene are insane and do some amazing work. But I just wanted to tell you some things that I learned along the way. So let's go into maybe the more interesting part. Okay, so how do we take all this knowledge, put it together, and convert a chip to code, maybe to an emulator? Well, let's look back at the chips from my piano, the one that I was talking about. And those are gate arrays. They present that repeated structure, and we know now, thanks to the spreadsheet and other work that other people did, what cells they're using. But we need some tooling. We need like software to help us doing that. So what is the best software that I came up with to work with silicon? Well, of course, JavaScript and Inkscape. I mean, that's the standard of the industry. And why those? Because it allowed me to draw on top of the picture, draw vectors, then import them into a script and do stuff with the script and maybe automate some of the process. The first thing that I did is annotating all the cell boundaries, which means finding where each cell is. Basically, to do this, you need to find all the domains that do not connect between each other and just connects externally. And once I did this, I ran a script that allowed me to crop all those areas, and I got some nice pictures of all my gates. And with that, I just manually put them in the right folder, so that I ended up with like 30 different kind of cells, which was actually not too much. So that was something that it didn't make sense to automate further. And then for each cell, I annotated what is the cell configuration. Suppose that you have an AND logic port. You want to annotate where the input 1 and the input 2 and the output is. Or if you have like an adder with 4 bits of input, you need to annotate where all the inputs and outputs are. I did that with Inkscape just by placing a circle on top of the input and output area, and you will see later why I did this. Then came the most tedious part, which was annotating the wires, and for each chip this took like 3 days of work. So it was a bit tedious, but it was not the end of the world. The problem was that the first time that I did it, I couldn't figure out a few things, so I did some mistakes. So I did the first, the second, the third, and then I did the first one again because there were too many errors. And trust me, I tried to automate this. You have to do it by hand, basically. And then we take all the data that we collected previously, the boundaries of the cell, where the inputs output are, and the wires, and we see where they intersect. So that this way we're able to make a list of cells, what they are, what are the IDs that are going into inputs, and what are the IDs that are going into output. In technical terms, this basically means recovering a netlist. So this way, we are basically recreating a schematic of the circuit. And what the thing that I did here is that I wrote a small code generator, which took all the annotation that I did and outputted the Verilog code, which is a complete mess right now because it was every single thing put together without names. And I converted all the logic parts into expressions so that maybe I could figure out things from here. And then I started refactoring. I started going backwards from what I knew. I started giving name to things. One thing that you do sometimes is figure out what some values in RAM are meant to be, what is the configuration. And you can find the cycle counters. And the cycle counters is an idea that chips do things in different times. For example, they don't process everything at once, but they do something in the first cycle, something in the second cycle, something in the third cycle, and then they loop back. And if you find a counter and you find a decoder, which decodes every possible cycle, then you can basically figure out what the chip is doing in every step of the process. And so that's another thing that you can figure out from the chip. And another thing that you can figure out is the chaining. If you have a bunch of 4-bit adders, it could be that they're actually one big adder, just that they're connected with the carry input and carry output. And this way was further able to refactor my code and figure out more about how it worked. This also works with memory units. Like if you have a memory that is 32 bits, you're forced to use a bunch of 4-bit cells, and then you can basically figure out that actually it's just the same data, but it's divided in parts of 4 bits. So that's another thing that you can figure out. Another weird thing that I found was that there was some very long combinatorial operations that actually were doing a giant lookup table. Like I tried to plot the output of that thing, and an exponential function came out. So sometimes even some ROM is implemented by using logic parts, which is a bit weird, but it was cool. And another thing that I figured out, because apparently the manufacturer of that thing really didn't want people to mess up with it, they use scrambling. You know that if you have a ROM, you can wire the data and the address line incorrectly, and it will still work perfectly because the ROM doesn't care how it's wired as long as you put the correct data inside. And what they did is that they connected the ROM wrongly on purpose, so that if you read it normally, it would be complete garbage. And they even put a not on some data and address lines, so that either you try all the possible combinations, or you dump the chip into acid, which is the other way that apparently is more efficient. And so I put all this work together. I decap the chip, I found all the logic parts and how they're connected together, and I ended up with the source code, the assembly of the chip. So at the end, those complicated algorithms and computation done on a mainframe, how did that piano work? Did it actually use some fancy mathematical thing, modeling, physical modeling, whatever? No, of course, it was a sample player. I mean, what do you expect? It worked exactly like the sound chip of a Super Nintendo, or it was even simpler than that, because it didn't have, it had 2 points interpolation instead of Gaussian one. But yeah, this was my journey into figure out magic tech that was supposed to be very complicated. That actually turned out pretty simple. And I learned how to look at silicon and find something out from it. But I wanted to quickly talk about what didn't work. I tried to simulate the circuit, and simulation, either you have some perfect output, but even if you have some small mistakes, then nothing will work. So that's a thing that basically I tried, and then I couldn't figure out where the error is, so I just looked into the code directly. Another thing that I tried is that instead of automating everything, I tried to reconstruct a schematic for the chip in KiCad. And after 2 hours of work and covering like 5% of the chip, I figured out that it was time wasted. And so I said, let's automate this as well, since KiCad format, it's text-based. So I pretty much outputted the entire content of the chip as it is on a KiCad schematic, but then I had to connect the things together, and even if I did that automatically, then I would still have had to recombine no, it was too complicated, so Verilog worked very well. Another thing that I saw other people doing is using computer vision to recognize the cells themselves instead of doing it manually. Which I didn't do because recognizing the cells at the end was like something like 1 hour of work, thankfully. And the last thing that I didn't even try was like trying on the wires, which was way too complicated. Like you can see that you can sometimes barely, even by human eye, figure out what is going on here. So I would have had to train a machine learning model and make it work on this kind of data. So I figured out that I could just raw dog it and annotate all the wires by hand. What worked though, it's the conversion of SVG to Verilog with scripts and Inkscape, which proved to be a bit buggy, but an amazing tool for just annotating images and figuring out stuff from it. So the last thing that I want to talk about, I mentioned before the Fujitsu standard cells, which I still have no idea, most of them, how they work. But we know how that chip works, which is a chip from an NES cartridge. So what I plan to do is trace the chip, figure out the cells, and figure out the cells backwards from the fact that we already know how the chip works. And so that's one thing that I will try to do eventually to figure out the Fujitsu standard cells. So I wanted to say thank you for listening to my yapping. Do we have time for questions? Do we have time for questions?
Yeah.
Perfect. Anyone? Yes.
Hello. Did you find any clever information encoding techniques for the samples?
Oh yes, they were encoded exponentially. The idea is that it does volume modulation, and if you want to modulate the volume of a sample, you need to multiply it by a value. Just the multiplication is expensive. So what they did is that they exploited the fact that in an exponential space, the multiplication becomes an addition, and they store all the samples as powers of 2's, and then they use a lookup table to reconvert them to linear. And a lot of other stuff like that.
Yeah.
How many samples were there?
It's cool because all those samples are limited to a size of 2048 samples in total, so there were a bunch of single cycle waveforms that were played together, and in the ROM it was like 20 samples, I think, just that they were cleverly combined together. Yes?
No. Hey, thanks for the nice talk.
Thank you.
More or less 2 questions, if there's no one else. First is, did you figure out what feature size those, or what technology size those chips were? I mean, this were optical images, what size?
Oh, I should have prepared about that because I have no idea. And the chip is pretty large. And those pictures that you saw were taken with a 20x magnification.
Okay.
So it's pretty big. It's the master slide is from 1985, so they didn't have amazing technology back then. But yes.
And the second question, if you were to do this all over again, is there a thing that you would do differently? Anything where you said, oh, I would have loved to know this before I started?
Yeah, I mean, that's a bit of a question that is like, what if history could be changed? I don't know, because I'm happy with the process that I arrived to, and if I could have done it from scratch, I would have liked to know all the cells beforehand, which, of course, but yeah.
Cool, thanks.
Thank you. Yes?
Hi. Yeah, thanks also from me for the talk. You mentioned that you did this a lot with older circuits. Is this also possible with like more contemporary ICs?
Contemporary, do you mean like 2000, 2010, or 2024?
All of them?
How much money do you have? Do you have access to an electron microscope? Because if the answer is no, then it's going to be really complicated.
Well, the question is first, is it possible? Because it might be worth it.
I think it is. Just that the sheer amount of work that you have to put into means that it's not something that a person can do. I don't think so.
Okay, so it's more a magnification question and not something like modern silicon manufacturers kind of mask the circuits.
I mean, yes, it is a question of magnification, but if you make things smaller, it also means that you're making them more complicated. You're putting more transistors there. And that thing was like 8,000 transistors. Modern CPUs have like billions. So it's like trying to reverse engineer a program that is like a 300 megabytes binary full of obfuscation. So I think that everything is possible, especially if you have the right tools. The problem is really putting the effort in to figure out what is going on there.
Mm-hmm. Okay, thanks.
Thank you.
Well, let's thank the speaker again. Thank you.
Thank you.